So at first glance, there's not a lot in common between a big airplane and a small seashell. But if you look in really closely, these are both very complex things. So the shell in particular is a mollusk shell, and it's comprised of a material known as nacre, or more commonly known as mother of pearl. That's that kind of shimmery inner layer. So nacre is very unique in this materials world because it combines two very discrete material properties, one being strength and one being toughness. These are two things that are not very common in one body. An example is something like concrete. Concrete is very strong, it can bear loads, but if you stretch it or shake it, it collapses or falls apart. That's why it's not great to use in earthquake building. Another example is something like a balloon, a latex. It's very stretchy, but if you try to apply a load to it, it breaks. You pop it, it pops. So it's very tough, but it's not very strong. So combining this strength and toughness in one body in this shell is very unique in this material property world. It's done in such a way called a brick wall or brick and mortar structure. And the structure, if you zoom in, looks just like that, a brick wall. And there's these bricks that are made of what's called calcium carbonate, and they're very strong. And there's this matrix of polymers and proteins in a mortar setting that allow these bricks to stretch and flex. And so in one package, you have strength and toughness. What I do in my lab at Stony Brook is we work on a technology called thermal spray deposition. And this is an unrelated technology. It's used for coatings, and it's primarily used in things like aerospace. And so we can put these coatings in jetliner engines, and they insulate the engine. They keep it really nice and hot, but they keep the surrounding metal nice and cool. It works out for increased efficiencies. And if you it turns out that if you zoom in and look at these coatings up close, they bear a really striking resemblance to the structure in the nacre. And so we decided, can we take a mature technology and use it to develop a synthetic nacre variety? And so what we did was we sprayed a large sheet of this, we backfilled it with polymers, epoxies, and even in some cases metals, and created the synthetic nacre. And so this is unique in a few reasons. One is that it allows us to do a really large-scale deposition. So in traditional lab-scale manufacturing of synthetic nacre, you can make little 1-inch samples of nacre. Not very exciting. But with our technology, we can coat big, large areas, so sheets, and make the stuff. So it makes it more viable in an industrial scale. The second is the values of toughness and strength that we test with our synthetic nacre end up being some of the highest reported in the scientific literature. So our values for strength and toughness are among the highest of any of these synthetic nacre varieties, which is pretty cool. And third, although we're not using these direct synthetic nacres in the engines, we can study these coatings in the engines with the same methodology and same scientific framework that we can look at the nacre with. So what I do in my research specifically is looking at things like crack progression and brittleness in these ceramic coatings in the engines to better understand how these materials can be improved upon and further developed, which ultimately result in a safer, more efficient, and cheaper airplane flight for you guys. So thank you.
Okay, Gregory Smith.